All right, so today will be the beginning of probably what will become 2 videos to cover the topic of linear regression. This is probably one of the few times in class that we're going to deal with bivariate data, meaning 2 variables. This topic is the same for Math 220 and Math 307, so just kind of keep everybody organized, which chapter you're in, and you do need to have out a handout because we're going to be putting data into our TI-83 about halfway through. Let me write some things first, and then we'll talk about it. All right, so on the top of my head, bivariate data, trying to see not only is there a relationship between 2 variables, but if there is, how strong that relationship is, and then to actually describe it with a linear equation. So bivariate means 2 variables. So thinking about one more graph would be the scatter plot. Think your XY data points like you probably would have started plotting on graph paper in Algebra 1, right? Scatter plot of your XY points. Now, throughout Algebra 1 in high school, it always seemed like your teacher always made you show the origin. You could always see where the X and Y axis was intersecting at the origin. You don't actually have to have that on the graph. Think about if we're looking at the relationship between used car prices and how many miles are on that used car, right? Well, you're talking tens of thousands, if not 100,000 miles on a used car. And then the prices would also be, even in the thousands. If you try to show 0, 0 on the graph, what's going to happen is going to bunch up the data. It's going to become this glob, and you're not going to be able to see the pattern. So you kind of basically are trying to just zoom in to where your data points are. Throughout this, you're going to hear me use the words, is there a relationship between the 2 variables? We might say an association or a link or a relationship. Those are all correct and appropriate words, right? But this does not mean causation. The only way we can ever tell if one variable causes the other is by a very controlled experiment. Most of the stuff that we are, see in the media and that, we're exposed to are actually basically observational studies. There was no control. So you can talk about links and associations, but it doesn't mean one causes the other. At some point in the last few weeks, I may have used that example, silly example, extreme example of shark attacks and ice cream sales. It would be a great positive relationship between the two, but it doesn't mean one caused the other. Both of those are related to summertime temperature, right? So talk about links and relationships. Now, let's go. So the first, 20 or 30 minutes here are kind of intro, background. I'm actually going to take a little bit of liberty right now, and I'm putting 2 graphs on one, okay? So you wouldn't put 2 graphs on one in real life, but I'm just trying to show you, let's say that was your data set, or let's say that was your data set. Both of these are a perfect positive relationship. And relationship is going to get spelled so often, I'm going to shorten it up to RELN. And what do we mean by perfect is how well the data points fit a straight line. So humor me, pretend that I drew them in a perfectly straight line. Okay, that's perfect, and that's perfect. That is as perfect as that. That is as perfect as that. Basically, steepness, maybe I should write that in another color. Steepness does not matter. A lot of students, for some reason, think the steeper one is somehow better than the flatter one, and that is not the case. And positive, we're kind of getting that idea of slope, right? As x increases, y increases. So that's why we're going to call it positive. Of course, we have the opposite. Again, I'm trying to make it perfect on a linear line. This would be a perfect negative or inverse, whichever word you prefer, relationship. Perfect negative. So again, when we talk about the strength of the relationship, we're talking about how well the data points are lined up on a linear line. Now, unfortunately, in real life, nothing looks that good, right? You don't have to write this down, but just, in real life, we're going to be dealing with snowstorms, okay? And again, don't write this down, but eventually we're going to try to figure out which linear line describes the snowstorm the best. Okay, now we were talking about the strength, right? I've been using that word. Let's get a little more formal now. This is a first symbol or letter. We have to know what it means. Something called the correlation coefficient. It is denoted by R. So this thing called correlation coefficient, it measures the strength and the direction of the linear association between the two variables. Luckily for us, the calculator is going to give us the value for R, but we still need to know what it means and how to interpret it. R runs between -1 and 1. So remember our perfect positive relationships? That would have been an R of +1. Remember our perfect negative or inverse relationship? That would be an R of -1. Those are the two extremes, right? Now, often in books, they'll show you a picture, like of a little snowstorm, and the authors will suddenly say, oh yeah, that looks strong. Or they'll say, yeah, we had an R of 0.7. They'll start to interpret it, and you as a student will wonder, well, how'd they know that? So a very common rule of thumb that most textbooks give you, I'm going to put up here. This is not a set in stone thing, but it's a widely accepted, hey, it gives you the big idea. Oops. Yeah, that's R. -1 to 1. We cut it at the 0.5s and the 0.8s. Anything between the 0.5s is weak. Anything between the 0.5s and 0.8s is called moderate. And anything between the 0.8s and the 1s is called strong. So this is the very beginning to try to start to describe the strength of the relationship between the two variables. Little aside here. For example, there is nothing special about being a positive number. A lot of students think somehow negative is bad and positive is good. That's not the case at all. A negative relationship, well, the more you drive, the less gas you have in your tank, right? So the negative just means as one goes up, the other goes down. So make sure you understand that negative 0.5 is a stronger relationship than positive 0.83. Now here is something that is true. It has some pros and cons to it. Part of all these word problems we're going to practice, it's very easy, but you're going to have to identify which is the x variable and which is the y variable. And if for some reason you got them backwards, you would still get the same R, the same correlation, the same strength of the relationship. Now, that sounds like an advantage, right? The disadvantage is, though, when you go to actually get the equation of the line, your line would be completely wrong. So you do need to make sure you know how to figure out what's the x and the y variable, but no matter, the R would be the same. And just to remind you, because in case you're Googling or looking at a textbook, they usually give you terrible formulas to calculate the R by hand. RTI 83 is going to give us R. Right. Well, we have a little bit more to do before we even ever start doing a problem, right? Some other things to talk about. We need to get some synonyms up first. And then I am going to give you a little bit of background, I hate to call it theory. We're going to approach it visually. But there is something called the principle of least squares. Now, all of that sounds very confusing. Principle is a very formal word. Least squares, what the heck does that mean? Well, let me list a bunch of synonyms first. You don't have to draw this picture. But remember I said we were going to have, some little snowstorm, right? And again, you do not have to draw this. Now, if I had students in front of me and if I gave you guys some different colored pens, someone might come up and say, oh, I think that line looks pretty good to describe the data set. Someone else might come up and say, well, I think that one is better. Someone else might come up and say, yeah, those look good, but I think that's the correct one, right? And all three of those look pretty good to describe that snowstorm. Now, hopefully nobody would draw their line down here or up here, right? That doesn't even make sense. That's not where the data set was. Even in this small area, there is an infinite number of lines. Because think about it, we have slope and intercept that go into a linear line, right? So even in this little area, there's an infinite number of choices. Well, actually, though, there's only one correct answer. And that's what the principle of least squares is. How did they historically figure out the one line of best fit? So all of these are synonyms for what is the one line that describes that data set, that scatter plot, that snowstorm that I'm calling it, that best. So line and equation are synonyms of each other, so I didn't put up every possible combination, right? But line of best fit, linear regression equation, we're trying to give you know, the equation of a linear line. A lot of times people know we're doing linear, so they'll just leave it off, the word linear, and they'll call it the regression equation. It's also called the least squares line, or LLS for short. You'll see why it's called least squares in just a couple minutes. Or the predictor equation, because the whole point of doing this is so then we can predict for data points we didn't actually study originally. But here's where I want to take a minute to talk about. So this is called y hat. Maybe I should write that a little bit neater. It's y with like a little birthday hat on top of it. The little two sides of a triangle in mathematics means prediction. And I've just done a generic form of a linear line, okay? Now, this is where you have to make sure you understand. The A's and the B's are just placeholders. Most of us came off of high school with what? MX plus B. A lot of the stats textbooks are now using A plus BX, which really throws people because we grew up with M being slope and B being the intercept, right? Other books will do AX plus B, etc. It doesn't matter. Because I'm never going to ask you what is A, what is B, because it would be fair for you to say back to me, well, what do you mean by A and what do you mean by B? Most important thing, the only thing you have to know is what is connected to the X is the slope. What sits by itself is the intercept. So like in this one, that's the slope. In this one, that's the slope. And in this one, that's the slope. The TI-83 is going to tell you the appropriate notation, so you're not going to have to worry about it. All right, so those are just synonyms, because I use all those words interchangeably. It's, hey, can you please tell me the equation of the best fitting line, right? But how'd they ever figure it out if there's an infinite number in there? What was the criteria for deciding that one line was better than another? All right, that is the principle of least squares. Let me get a scatter plot up here. I'm just going to make a sloppy one. I'm going to put my line through it, and I'm just going to focus on one of the data points. It's like I've zoomed in. Whatever I say about him, I could say about any of the other ones, right? And this is representing my best fitting line. So think about if this was a data point. This would have been my original data point, xi, yi, just one of my xy coordinates for my data set, right? And I would have graphed it, and I would have put my little dot. Okay. Well, look at this, though. If you put that x into the predictor equation, it's actually predicting the y to be way down there, okay? So, see how the line didn't go through that data point? Your best fitting line may not go through any of your data points, or you might get lucky. It might go through one or two of them, but you know, it can't go through the whole snowstorm, right? So, it did not go through this data point. It predicted it to be way down there. So, it missed its mark, right? See this distance? That amount is how much it was off. Very informally, this is called a mistake, but you're never going to see that word in a math book, right? They like to use the more formal word called an error, which is very hard for me to pronounce. Technically, so I'm giving you a bunch of synonyms again. This is not my fault. Every book will use all of these words. This error, how far off the line you were, another way to say that is a vertical deviation. I've deviated from where I was supposed to be, right? Because I missed my mark. And see how that's the vertical distance? Okay. Then eventually books will get around to telling you that that's actually a vocabulary word called a residual. So this is important. You're going to be calculating residuals on the homeworks. The residual, just visually, is how far off each data point is from the line. I've shown you in picture form, but maybe we should actually write the formula for it. The residual is y minus y hat. That distance, how far off the mark it is. Now, here's a residual, and here's a residual. Here's a little residual. Here's a residual. Here's a residual. Here is one. If you have 10 data points, you have 10 residuals, right? If your line actually went through a point, you know, maybe I had a point right there and the line actually went through it, then the residual would be 0. But you're going to have some positives and some negatives, right? Because when the y is bigger, y minus y hat, that would be positive. If the if it's down here, then it's going to be negative. That all is going to play into the next part that I write up here. But residual, so if you have 10 data points, you would have 10 residuals. I will never ask you to calculate 10 different residuals. If you can calculate one residual, then, you know, given enough time, obviously you could calculate the rest of them. What has this got to do with how did they figure out the equation of that line? Well, maybe I'll try to write here in case I want to point to my picture again. You know, it probably makes sense that we would like to keep mistakes as small as possible, right? I mean, just in life, we don't like mistakes. It's a bad thing. So, if we could, so remember our mistakes are our residuals, how far off we are. So what about if we added up all of the residuals? The only problem with that is my positives and negatives would end up canceling out to 0. We saw the same thing when we were talking about standard deviation. So, I don't know if you remember back then, but we love to square things. There's this real fancy, and this is probably why people don't like mathematics, because we talk all formally. Sum of squared deviations. Basically, it's the sum of the residuals squared, right? Because that's what my residual is. That's the distance for each data point. But we're squaring them so my positives and negatives don't cancel out. So that's the only reason we're doing that. And then we're adding them all up. If we have 10 data points, we would be adding 10 different things. Good news is you're not going to be actually doing this by hand. But if we could make this as small as possible, remember earlier when I put up 3 lines and they all looked pretty good to me? Just for that red, blue, and black line that I had put up, if you could go calculate the sum of the residuals and pick the line that has the smaller pile. It's like we're throwing all the mistakes into a pile and we're picking the line that has the smallest pile. Well, here's the problem though. I drew 3 lines on that graph a few minutes ago, but remember how I said there was actually an infinite number? Well, none of us have time to check an infinite number of lines, right? That's literally impossible. And it doesn't matter if you've ever had calculus, but calculus basically is the mathematics of infinity. Calculus does have the techniques, I'm taking some freedoms here, but to check an infinite number of lines and to find the line that has the smallest. If you've had calculus, setting the first derivative equals to 0 is a way to minimize, so it has to do with that stuff. But basically every book will kind of say, from the results of calculus, because we can't show you that. It's way too complicated, and this is not a calculus-based course. But from the results of calculus, they figured out what the equation was for the slope in the intercept, and guess what? That's been programmed into every computer and every calculator, so you're not going to be doing that stuff by hand. But that's how they originally figured out what the one line of best fit was. That was the criteria that they used. Few other maybe random but important comments before we actually practice a problem. How are you going to be able to know what's the x variable and what's the y variable? This is the way we talk in mathematics. We predict y based on x. So if I said predict car price based on mileage, you'll just line them up and you'll know which variables are which. Again, we're going to use this line for prediction purposes, to be able to predict for values we had not originally studied, but there are some limits to that. You are not allowed to predict outside of the original X data range. Again, you don't need to draw this, but let's say your scatter plot's here. So it means I have looked at X's from there to there. You're not going to be allowed to predict for something else. And as usual, photo booth likes to glitch on me. I'm going to have to stop the video because I know you cannot see me, but you can hear me, and I'll make a second part.